In recent times, we have seen scientists developing numerous types of robots, from sized robots that can bust some moves and bird-inspired robots to micro-robots that work in swarms. In this regard, Northwestern University engineers have developed the smallest ever remote-controlled walking robot, and it comes in the form of a tiny, adorable peekytoe crab. Just a half millimeter wide, the tiny crab can bend, twist, crawl, walk, turn, and even jump. The researchers also developed millimeter-sized robots resembling inchworms, crickets, and beetles. Although the research is exploratory at this point, the researchers believe their technology may bring the field closer to realizing micro-sized robots that can perform practical tasks inside tightly confined spaces. Last September, the same team introduced a winged microchip that was the smallest ever human-made flying structure. Smaller than a flea, the crab is not powered by complex hardware, hydraulics, or electricity. Instead, its power lies within the elastic resilience of its body. To construct the robot, the researchers used a shape memory alloy material that transforms to its remembered shape when heated. In this case, the researchers used a scanned laser beam to rapidly heat the robot at different targeted locations across its body. A thin coating of glass elastically returns the corresponding part of the structure to its deformed shape upon cooling. As the robot changes from one phase to another, deformed to remembered shape and back again, it creates locomotion. Not only does the laser remotely control the robot to activate it, but the laser scanning direction also determines the robot's walking direction. Scanning from left to right, for example, causes the robot to move from right to left. To manufacture such a tiny critter, these scientists turned to a technique they introduced 8 years ago, a pop-up assembly method inspired by a child's pop-up book. A pioneer in bioelectronics who led the experimental work, Rogers said, "With these assembly techniques and materials concepts, we can build walking robots with almost any size or 3D shapes." While Huang, who led the theoretical work, says, "Our technology enables a variety of controlled motion modalities and can walk with an average speed of half its body length per second. This is very challenging to achieve at such small scales for terrestrial robots." Speaking of tiny robots, researchers from North Carolina State University and the University of Pennsylvania have developed soft robots that are capable of navigating complex environments, such as mazes, without input from humans or computer software. The soft robots are made of liquid crystal elastomers in the shape of a twisted ribbon, resembling translucent rotini. When you place the ribbon on a surface that is at least 55 degrees Celsius, which is hotter than the ambient air, the portion of the ribbon touching the surface contracts, while the portion of the ribbon exposed to the air does not. This induces a rolling motion in the ribbon, and the warmer the surface, the faster it rolls. Co-author Yin states, "These soft robots demonstrate a concept called physical intelligence, meaning that structural design and smart materials are what allow the soft robot to navigate various situations, as opposed to computational intelligence. The soft robot we've made in a twisted ribbon shape is capable of negotiating these obstacles with no human or computer intervention whatsoever. The ribbon does this in two ways. First, if one end of the ribbon encounters an object, the ribbon rotates slightly to get around the obstacle. Second, if the central part of the robot encounters an object, it snaps. The snap is a rapid release of stored deformation energy that causes the ribbon to jump slightly and reorient itself before landing. The ribbon may need to snap more than once before finding an orientation that allows it to negotiate the obstacle, but ultimately it always finds a clear path forward." The researchers conducted multiple experiments demonstrating the ribbon-like soft robot is capable of navigating a variety of maze-like environments. The researchers also demonstrated that the soft robots would work well in desert environments, showing they were capable of climbing and descending slopes of loose sand. Yin further added, "This is interesting and fun to look at, but more importantly, it provides new insights into how we can design soft robots that are capable of harvesting heat energy from natural environments and autonomously negotiating complex unstructured settings such as roads and harsh deserts." In another discovery, researchers from Carnegie Mellon University took an all-terrain vehicle on wild rides through tall grass, loose gravel, and mud to gather data about how the ATV interacted with a challenging off-road environment. They drove the heavily instrumented ATV aggressively at speeds up to 30 miles an hour. They slid through turns, took it up and down hills, and even got it stuck in the mud, all while gathering data such as video, the speed of each vehicle, and the amount of suspension shock travel from from 7 types of sensors. The resulting dataset called Tartandrive includes about 200,000 of these real-world interactions. The researchers believe the data is the largest real-world multimodal off-road driving dataset, both in terms of the number of interactions and types of sensors. The 5 hours of data could be useful for training a self-driving vehicle to navigate off-road. Previous work on off-road driving has often involved annotated maps, which provide labels such as mud, grass, vegetation, or water to help the robot understand the terrain. But that sort of information isn't often available, and even when it is, might not be useful. A map area labeled as mud, for example, may or may not be drivable. Robots that understand dynamics can reason about the physical world. The research team found that the multimodal sensor data they gathered enabled them to build prediction models superior to those developed with simpler non-dynamic data. Driving aggressively also pushed the ATV into a performance realm, where an understanding of dynamics became essential, explained the lead author 𝙭. Though most work on self-driving vehicles focuses on street driving, the first applications likely will be off-road and controlled access areas, where the risk of collisions with people or other vehicles is limited. Another researcher, Wang, added, unlike autonomous street driving, off-road driving is more challenging because you have to understand the dynamics of the terrain in order to drive safely and to drive faster. Meanwhile, in the domain of AI, University of Exeter scientists trained an AI to learn the Coral Reef Song using multiple recordings of healthy and degraded reefs, allowing the machine to learn the difference. Coral reefs have a complex soundscape, and even experts have to conduct painstaking analyses to measure reef health based on sound recordings. The computer analyzed a host of new recordings and successfully identified reef health 92% of the time. The team used this to track the progress of reef restoration projects. The fish and other creatures living on coral reefs make a vast range of sound. The meaning of many of these calls remains unknown, but the new AI method can distinguish between the overall sounds of healthy and unhealthy reefs. The lead author Williams says coral reefs are facing multiple threats, including climate change, so monitoring their health and success of conservation projects is vital. Our findings show that a computer can pick up patterns that are undetectable to human ear. It can tell us faster and more accurately how the reef is doing. Besides this, veterinarians and researchers at the University of California, Davis School of Veterinary Medicine have discovered a technique to predict a life-threatening disease in dogs through the use of artificial intelligence. Leptospirosis is a disease that dogs can get from drinking water contaminated with Leptospira bacteria, can cause kidney failure, liver disease, and severe bleeding into the lungs. Early detection of the disease is crucial and may mean the difference between life and death. After many months of testing various models, the team has developed one that outperformed traditional testing methods and provided accurately early detection of the disease with a 90 to 100% success rate. The goal for the model is for it to become an online resource for veterinarians to enter patient data and receive a timely prediction. Lead author Reagan says, as we move forward, we hope to apply AI methods to improve our ability to quickly diagnose other types of infections. While the school's team, Statter says, AI-based clinical decision-making is going to be the future for many aspects of veterinary medicine. I am thrilled to see the UC Davis veterinarians and scientists leading that charge. We are committed to putting resources behind AI ventures and look forward to partnering with researchers, philanthropists, and industry to advance this science. That's it for this episode. Do let us know your valuable thoughts on these robotics and AI discoveries in the comments.